Okay, now as we said at the end of the last video, clearly then y equals x squared would have just plain old x squared. It would have no x and no constant term. So just y equals x squared would have a 1 in front of the x squared and zeros in front of the other terms, and would therefore be represented by the column vector 1, 0, 0. We'll call that vector v1. So now v1 is this column vector, and very clearly in this context this vector stands for 1x squared plus 0x plus 0, which is just plain old x squared. Similarly, y equals x, there's no x squared, there's an x, there's no constant term. That's our vector v2. And the vector, or the function y equals 1. That is a quadratic polynomial, but it has a 0 coefficient here, 0 coefficient here, and just the number 1 here, represented by the column vector 0, 0, 1. Okay, now we ask if, well, we simply ask what the sum of these vectors is. I thought we were solving an equation, answering a question, but we do that later. It's been a couple of days since we did this in class. So what is the vector 4v1 plus 7v2 plus 3v3? It's called a linear combination of these three vectors. We just add multiples of the three vectors. That forms what we call a linear combination. Well, we represent v1 as 1, 0, 0, v2 as 0, 1, 0, v3 as 0, 0, 1, and we do 4 times this plus 7 times this plus 3 times this. Well, 4 times this gives us 4, 0, 0. 7 times 0, 1, 0 gives us 0, 7, 0. 3 times 0, 0, 1 gives us 0, 0, 3. And then we add those up, we get 4, 7, 3. And this represents the linear function y equals 4x squared plus 7x plus 3. And not the linear function, the quadratic function. Y equals 4x squared plus 7x plus 3. Okay, just an example of a linear combination of three vectors and three naturally representative vectors that could easily be added to give us another vector representing another polynomial.